answer is actually A. And I'm glad that you guys narrowed it at least down to A or C, because as you know, they asked what the acceleration of the toy was. And if you look at the units, you can already eliminate B and D because these are in newtons. So that was easy. Now all you have to do is just find what the acceleration actually is. Okay, so we know that the weight of this, or the mass of this, I should say, weight is different from mass. Mass is 2 kilograms. So I don't know if I stressed this yet, but the first step to solving any force problem is always make a force diagram. So using all the known forces, we know that gravity always downward, mg, normal force always upward, and in this case also mg, because it's directly opposing. Actually, I shouldn't say that. Clear, yeah. Sorry about that. Gravity going down, there is a normal force. So we'll just call it Fn for now, along the ground with an applied force of 10 newtons. So we know that there's a force this way of 10 newtons. And a frictional force of 1 newton. And we know that if he's sliding it to the left, friction always opposes motion. So friction is going to the right, and it's F of 1 newton. Okay. And ask what is the acceleration. So to find acceleration, you just have to kind of break it down into components and find the net force. You find the net force especially in this axis. And once you do that, you can use F equals MA. Right? So first thing we have to do is we have to break this down into components, and that's what the angle is for. What we're trying to find is this spot. We'll just call this X, this component, right? And we know that when we have this angle, we know this is the hypotenuse. So we know that cosine 60 is equal to X over the hypotenuse, which is this one, which we know is 10. And you do have to memorize that cosine of 60 is 1/2, and that sine of 30 is 1/2. So 1/2 equals X over 10, and you know that X equals 5. So it's a force of 5 newtons to the left. The only force in that other force in this axis, this left and right axes, is friction, which is 1 newton in the opposite direction. So you subtract, it's 1 newton. So 5 newtons minus 1 newton, and you get a total of 4 newtons equals M, which we know is 2 kilograms, times A, which is also 2, because 4 divided by 2 is equal to 2, and A is the correct answer. Does that make sense? Does that make sense to everybody? It's very, very straightforward, very simple. The only difficulty that I would see in this question would be if you would be getting tripped up with the angles, the 60 degrees. Remember SOHCAHTOA, 60, this one is adjacent. So you're looking for the adjacent, right? Because it's adjacent to this is the hypotenuse. So use cosine, and you know that cosine of 60, you have to memorize cosine of 60 is equal to 1/2. So 1/2 equals adjacent over hypotenuse, which you already know, and you can solve from there. Any questions? Okay, so I'll set up the algebra.
If it's F equals MA and A is equal to F over M, the F on top, is that tension minus cosine of 60? Like, could you set it up where we can literally—
Yes, I'll do that very quickly. Okay.
Belongs to.
So you know this is
M, and the F is going to be the friction minus cosine of 60. That's what we're trying. Yeah.
Okay. Yep. This is equal to force friction equal to 1 newton. This is equal to this is this component. This left thing is this is the axis we're working on. this axis. This is the x component of this force, right? This is the x-axis of this force. So we know that this is 10 newtons. Again, we set up our triangle like that. Then we do cosine of 60. Oh, sorry, it's s cosine 60 equals x over 10. That's because this is x. If we're just calling it x, over 10 newtons, this hypotenuse adjacent. We know that cosine of 60 is equal to 1/2. We simplify that. 1/2 is equal to x over 10. We solve what is x? Well, x is 5. So we know that x equals 5. So we know that the x component, so I'm going to redraw this. So we know the x component, this is the box. This is the guy pushing on it, pulling on it. So we know that the x component of this force is 5 newtons. We want to find out what the acceleration is. Obviously, if you're just pulling something along the floor, it's not accelerating up or down. So that means the F net in the y direction is 0 because it's not accelerating up or down. We know that because of F equals ma. If a equals 0, F has to be 0. However, it's accelerating to the left because he's pulling on it. In the direction he's pulling it, F is not equal to 0. That means a is not equal to 0. So we know that he's pulling on it with 5 newtons of force, but he's also being opposed by 1 newton of friction, right? So we want to find out what the total net force is in this xy plane, in this x plane, in this plane along this, right? So from here to here, we want to find out what the net force is in the x direction. Well, if it's going 5 this way and 1 this way, the result of these two together is just 4 in this way, right? So if you pull with 4 newtons and somebody opposes you with 1 newton, you're still in the end pulling with 4 newtons. So the total is 4 newtons. At the F net, the net force in the x direction is 4 newtons to the left, specifically to the left. So we can now use the formula F equals ma, Newton's second law, to find out what the acceleration is, because we know what the force is, it's 4 newtons. We know what the mass is. They told us in the problem it's 2 kilograms. Only unknown is now acceleration, which we're trying to find. Now we can just do simple math. 4 newtons divided by 2 kilograms is equal to 2 meters per second squared, which is the answer choice. Yes, mass is always in this situation, mass is always in kilograms. In physics, generally it's in kilograms. In chemistry, sometimes it's in grams. If it were in grams, you would convert it, yes. Because Newton's also takes into account the fact that it's in kilograms. So if it's physics, you would always just keep it in kilograms. If it's chemistry, you keep it in grams. Yeah, as Tim said in the chat, when you're dealing with Newtons, you're dealing with kilograms.
Mark, I have a question.
Mm-hmm.
So can you explain that unit again? How did you get to newtons and kilograms?
Right. Do you know what the unit of force is?
Newtons.
Right. You know that the force is 4 newtons because it's a force. You know that the equation that we're working with is F equals ma. F is force. Force has units of newtons, therefore 4 newtons. M is mass. Mass has units of kilograms, 2 kilograms, because they told us what the mass of the toy was. It's 2 kilograms. 2 kilograms. Acceleration, you know that acceleration has units meters per second squared. That's the only thing we have left. Acceleration, 2 meters per second squared is the answer. And that's what the answer choice is. Does that make sense? Or
how did you cancel that out to get meters per second? I'm just trying to figure that out.
I see. Right, because newtons is not a standard unit. It's a unit of force. Newtons is And we can actually do this as an exercise to derive what the newtons is. Newtons is actually, and if you want to think about it, it's kilograms times meters squared. Oh, sorry, meters per second squared. This is what newtons actually is. These are the standard units of newtons. Kilogram meters per second squared. This is what a newton is equal to a kilogram times a meter divided by a second squared. Does that make sense? We just simplify it down to newtons because we don't want to write this every time. Does that make sense?
Yes, but how did you get to the final ending meters per second for acceleration?
Well, you know that the unit, what is the unit of acceleration?
Meters per second squared.
Well, that's how we know, because any acceleration, no matter in what situation, acceleration always has a unit of meters per second squared. Does that make sense?
Yes, I think so. Okay. Yeah.
Okay.
I have a question.
Please.
When it's asking for applied force, do we always know that that is the arrow that's pointing, like the diagonal arrow where you wrote 10N? Is that always what the applied force we should be looking for?
So, it depends. They'll try and label it as best they can. So if there's a string, they'll write T under the string. There'll be like a line, and it'll say like T under it, and that's how you know it's a string. The reason you knew this was the applied force is because this was just the only arrow in the picture, so you kind of just assumed it was the applied force because they mentioned that there was an applied force, and this is the only direction. But yeah, all forces are written as arrows. So like you saw, I drew I drew this to represent gravity, this to represent friction, this to represent the normal force. But this arrow represents an applied force, right? It's just because it was the only other force it could be. It was the only force it could be. You know it couldn't be normal force because normal force always perpendicular to the ground, gravity always down, friction always opposes movement. Does that make sense?
Yes, thank you.
No problem. Any other questions before we move on? Okay. So formula sheet. This is kind of like a summation of what we've already been talking about. So all forces, the general formula for forces is force equals mass times acceleration, F equals ma. For weight, Fw, force is equal to mg. Again, very similar to the basic equation, just using gravity as the acceleration. Normal force is F equals mg on a flat surface. It's also F equals mg cosine theta on an incline. So if we want to go back to our incline, I mentioned that this component is, well, it was W, but it's essentially just mg sine theta. So this component is mg cosine theta, right? And notice how on an incline, this box is not accelerating up or down. It's not accelerating at all on this axis, on this plane. And that means the net acceleration is 0. That means the net force is 0. That means whatever this component of weight is, the mg cosine theta, that means the normal force has to be equal to it, just in the opposite direction, right? Because they have to cancel out to make 0, right? So you know that if this is mg cosine theta, this also has to be mg cosine theta, just going in the opposite direction, right? That's how we figure out what the normal force is. On an incline, it's always just mg cosine theta, right? But there's no exact formula, and it varies by situation. Like in this case, I actually incorrectly said at the beginning, normal force is equal to mg. It's not, because if you notice, mg is going down. This one has a y component of, this is a y component of the applied force, right, of equal to 10, which is the applied force, times sine 60. So you actually, since it's not accelerating up or down, you have to add it together, this y component and Fn, and set them both together equal to mg. So in this case, mg is equal to Fn plus 10 sine theta, 10 sine theta, which in this case is 60, but 10 sine theta. So Fn, if you were to isolate it, is not equal to mg. It's equal to mg minus 10 sine theta. Does that make sense? Does that make, oh, I shouldn't delete that. There you go. Does that make sense to everybody? Normal force in this case is not mg, is not equal to mg, even though it is a flat surface, because there's another force here that's going up. These two forces combine equal mg.
So for mg, Mark, so that so the normal force is it's the same as when you're finding the sine of y over the hypotenuse of 10. Is that also equal to the normal force?
No, that's the applied force. No, because, okay, so the normal force is just the ground pushing up. The applied force is, you said the child was dragging his toy. So like this 10 is equal to is just the child dragging it. So the 10 sine theta is just the kid, like the force the kid is using to drag it. Does that make sense? And if you want to think about it this way, right? When you're dragging something, especially at an angle, and you're kind of lifting it a little bit up, the ground isn't using as much effort. The ground isn't applying enough of a force to cancel out gravity, because you're taking some of that burden onto yourself in order to drag it, in order to move it, right? Same thing if you're trying to like kind of like lift like something heavy, like the ground normally, if you're just not touching it, the ground has all of the weight on it. If you kind of like pull a little bit up on something, try and lift it a little bit, not enough to lift it off the ground, but just a little bit, the ground is not pushing up as much on the object, because you're also pushing up, you're pulling up a little bit on the object. So the normal force is less than if you just left it alone. Same thing in this situation. The kid is kind of like lifting it a little bit. So the kid plus the normal force is equal to gravity, instead of just the normal force being equal to gravity. Does that make sense?
A bit lost, but okay.
Is there anything like in particular that you?
So how would I solve to find the value of the normal force?
Okay, I'll show you. Sure, no problem. So I mentioned gravity. It's going down. Normal force going straight up, and then there's also this going up. Okay, this component. We know that this component is equal to 10 sine theta, right? This is equal to the normal force. This is equal to mg. Right? So do you understand that because there's two arrows going up and only one arrow going down, right? But the net, like when you add up all of the arrows together, they have to perfectly cancel out. So the two arrows together have to combined have the same value as the one arrow going down. Does that make sense?
So it's all of it is a net like force total. Is that what you're saying?
Net force is just the combination. A net force is always the combination of all of the arrows. It's just,
so that's what that is. It's the net. You're finding the net force to find the normal force.
Oh,
okay.
Well, yes.
Okay.
No, wait, you're right, because the net force is zero. Do you know why the net force is zero?
Because the normal force is canceling out the weight, right? W equals
well,
mg.
Yes, but that's not why. Why is because you know the formula we just talked about, F equals ma. In this formula, F is equal to just net, it's F net, right? It's net force. If there's no acceleration, if A is equal to 0, that means no matter what M is, F net is always 0. We know that the box isn't accelerating up or down. We know that the acceleration of the box, because the box not moving up or down. Because of that, we know that A is 0. If the A is 0, that means the F net is also 0. Again, if we know that the A in up or down is 0, we know F net in up or down has to be 0. If we know F net is 0, that means we know all up arrows and all down arrows have to cancel each other out in order to make an F net. When you add all of the arrows together, it has to be 0. That's why we know that these two arrows are going up, this one is going down. Because we know that they have to cancel out, we know that the two up arrows have to add up to be the same as the one down arrow.
Because there's no acceleration.
Okay, yeah. Yes.
Right?
Yes. That's correct.
And that's because they didn't give that to you. Now, if they had given acceleration, that would be a different.
Yes, it would be a different story. Yes. All right.
But there's velocity. Well, there would be, right?
Sometimes there, again, acceleration, that's a more tricky subject, and that's more you have to do by a base. Just because I don't want to hold up the whole class, and we still have a lot more to get through. If you have any questions, please come to office hours. Please email me. But I have to move on because we still have a lot more to go. Okay, sorry. Anybody else? Anything quickly? All right. So again, we mentioned normal force, spring force. Again, F equals kx. K is the spring constant. X is the distance that the spring is currently extended to, minus it's from the distance it is currently from its normal position. This is the normal position. This is the extended position. This spring can't compress, but if it could, you could also compress it. Friction is equal to mu times Fn. Mu is just the constant, and different surfaces again have different mu's. And mu is this like U looking letter. It's Greek. Again, so like ice would have a very, very low mu because there's no friction, whereas something like concrete has much higher mu, right? And depends on the surface you're having friction on. Mu, there's two different types. There's static and kinetic. Kinetic is when an object is already moving and it's usually lower. Static is when an object is at rest and you're trying to move an object that's at rest. It's usually higher. Tension, again, varies, no exact formula, just like normal force. Any questions on this before we move on? Any of the formulas, anything with force, before we move on to work and power? Sorry, I'm just checking the time. The clock's above me. Okay. Okay, let's move on.